Yeah, thank you very much. So this talk is about particle physics with neutrino telescopes. And when I hear the term particle physics, usually what I think about is stuff like this. So collider physics, Large Hadron Collider, testing the standard model, or if you're very lucky, even discovering a new particle like the Higgs discovery roughly 10 years ago. And in this talk, I just want to show you that we can do this type of physics also with neutrino telescopes. So I want to start with the detection principle of neutrinos in neutrino telescopes. Let's say you have an incoming neutrino, and somewhere in your detector, just an unsuspecting nucleus sitting around. What very rarely happens is they interact via the electroweak force. And if the energy is high enough, which it usually is, you shatter apart this nucleus, which results in a hadron shower. And of course, here you can have charged particles, and in some of the interactions, the outgoing lepton is charged, which means you get Cherenkov radiation. So this is the signal that we can pick up with our detectors. Now, in order to do that, there's a couple boundary conditions that you need to fulfill. You need a transparent medium, obviously. You also want it to be deep underground to shield from backgrounds. And importantly, you need a huge volume, because first of all, since these interactions are so rare, you get a much better chance of observing something if the volume is big. And these events, they can extend over hundreds of meters, and you want to try to contain them, so you want a huge detector. Basically, what this means, what you're left with is to deploy a detector in the deep water or the deep ice. This is just a world map for neutrino telescopes. And if you look here at the South Pole, we currently have IceCube running, instrumenting a cubic kilometer. In the very nice talk before, we heard a lot about Antares and KM3net in the Mediterranean. And there's also GVD in Lake Baikal. And there are also a couple of future projects on the way. So for IceCube, we have the IceCube upgrade underway, and then later the much larger Gen 2. There is something under construction for the Pacific Ocean, P1. And also very recently, this new proposal popped up on the archive about the telescope in the South Chinese Sea called Trident. If we measure something in neutrino telescopes, that's how it usually looks like an event. So this is just for a generic telescope. These are the detector strings with the optical sensors. And in this case, you had a neutrino interacting somewhere here and then going in this direction, well, the interaction products. And shown in these colorful blobs are the observations of Cherenkov light. The color indicates the timing from blue early to red late, and the size of this blob, usually what we mean by that is the charge or the amount of Cherenkov light. So what can you learn from these type of interactions? One thing you can try to estimate is the energy of the event. And this is relatively straightforward to understand. For more energetic events, you expect more Cherenkov light. So I put you here these two event displays from IceCube. On the left side, this is a GeV scale event with very sparse Cherenkov light. And on the right side here, you are at the PeV scale, where you basically almost light up the whole detector. So from that relationship, you can estimate the energy. Of course, in real life, it's a little bit more complicated, and we have actually statistically meaningful techniques to infer the correct energy for the events. So by having the energy of an event, you can already do physics. And if we look at the cross-section for neutrino interactions, here, this is just the normal neutrino nucleus scattering. That is just slowly rising with energy. But if you look at the anti-electron neutrino electron scattering, it's this curve here, and you see that you hit a resonance condition here, peaking at around 6 PeV, and this is a so-called glacial resonance. Glacial resonance means that you create an on-shell W boson that then subsequently decays. And by knowing the energy of the event, we can try to find that glacial resonance. And we have actually found one candidate in IceCube data. This is an event display, so it's a fantastic event. The estimated energy of that event, the reconstructed energy, is 6 PeV plus minus 0.7. And this plot here shows you actually the posterior distribution of the reconstructed energy. And if you compare that to what you expect from a glacial resonance that decays hadronically, this is shown in this blue curve. The two match very well, and it's a plausible candidate for a glacial resonance. But then we also went further, and we kind of dissected this shower here, and we found indication that there were muons present. And the muons are a smoking gun signature for a hadronic decay. So this makes a quite compelling case for a glacial resonance, which would mean that we have observed anti-electron neutrinos at these high energies. So you can go further. We also heard that in the talk before, there are different event topologies in neutrino telescopes. Usually we call those the tracks and the cascades. Tracks happen when you have an energetic muon in your interaction, and these muons, they can travel a sizable distance before they decay, so hundreds of meters. And while doing so, they emit Cherenkov light. So you get this kind of elongated signature in the detector. And this is considerably different from the cascade interactions, which are from electromagnetic or hadronic showers. So we can try to also leverage that kind of difference in the events. And for example, that allows us to reconstruct the so-called inelasticity. So we can separately estimate the energy of the cascade and of the track part of an interaction. And this allows you to reconstruct the Bjorken Y of deep inelastic scattering. This is just basically if you take the track energy and divide it by the total energy of an event. You see here, this is the reconstructed Y in deep core versus the true Y, and you can see that we can reconstruct that quantity relatively well, lying here close to the one-to-one line. Now, this means we can measure that as a function of energy, and this is shown over here. This is a very recent result from deep core at these lower energies here, these 3 error bars, and this is from a previous IceCube measurement at higher energies. And this is quite interesting because this allows you to, for example, study or compare different event generators and cross-section calculations. Going in further, we can add more information from our events. So far, we have only used the energy and the topology. We can also try to estimate the direction of an event. So for example, the azimuth and the zenith. It very fast gets quite complicated, so I don't go into detail about how we do that, but here are a couple of references. And here, these are just some performance plots, how well we can do that. This is for Antares. This is the reconstructed zenith angle versus the true zenith angle, and you see that you lie with most of the events here on the one-to-one line, so you can actually reconstruct that quantity quite well. This is a plot you have seen in the talk just before for ARCA track events, and this is a similar plot for IceCube events, also tracks at high energies. And you see that in all of these cases, we can attain a resolution of sub-degree, and for cascades, as we have also heard, it's a little bit more difficult and roughly an order of magnitude worse resolutions there. Now we can exploit these angular reconstructions, again, to measure cross-sections. And you can picture the Earth basically as a target to measure cross-sections. And if you think about that, if you can reconstruct the angle, you can say if a neutrino first traveled through the Earth, or if it didn't, or partially. And this is now the neutrino transmission probability. So if a neutrino interacts, it might get absorbed. And you see that for Earth crossing trajectories, you have kind of a sizable absorption starting at around 40 TeV of energy and above. And by exploiting this, you can measure cross sections, and this is shown here on the plot on the right. These are now measurements from 3 different data sets in IceCube as a function of energy measuring the cross section. You see, this is all consistent with standard model expectations. This is a calculation from CSMS in this dashed red line, which you might say, okay, it's a bit boring because it's all consistent with the standard model. But I also want to point out that here, this is a measurement of deep inelastic scattering cross-section at energies that are completely out of range for accelerators. We are talking here about the TeV to the PeV range. So I think this is quite a powerful test of the standard model. All right, so these are a couple of results about cross sections. I also want to talk about neutrino oscillations, so measuring neutrino properties. And this is a super short primer on neutrino oscillations. First of all, neutrinos oscillate, we know that, and this is due to the flavor eigenstates not being aligned to the mass eigenstates. They are, if you want to rotate from one basis to the other, you need this matrix here, the PMNS matrix, and this is how it looks like. Now, this is for illustration purposes, the very simplest case of an oscillation probability formula for just 2 flavor vacuum oscillations. This gives you the probability that an initial muon neutrino will oscillate into the electron flavor. You have this term here, this is from the mixing matrix, so from this matrix. Over here, this is the difference between mass eigenstates. the energy of the neutrino, and L is the length that it traveled. So I thought it would be fun to do a back of the envelope calculation here. Let's say we look at atmospheric oscillations. We know the mass splitting is about 2.4 times 10 to the minus 3. And we also know that the Earth diameter is about 12,700 kilometers. If you put these numbers in the term from the formula before, and then you just need to make sure you have the correct units, you get this here. And in order to measure these oscillations, or let's say to have the best chance to measure them, you want, of course, this term to be maximal. So the argument of the sine function should be pi half, right? You solve for this and you find the energy should be around 25 GeV for maximal mixing. This is the exact same information, just now a fully fledged 3-flavor oscillation calculation with matter effects and everything. This shows the oscillation probabilities again as a function of the energy in this axis and the zenith angle in this axis, so which is proportional to the travel length. This is the same 25 GeV from before. So you see at 25 GeV, the mu neutrinos oscillate away. So this is something we can measure. We call this the mu neutrino disappearance. And of course, they just oscillate into a different flavor. So we expect them to arrive in the tau flavor, and this is also something we can measure. And what you see over here, this is enhanced mixing from matter effects with the electron neutrinos. This is something we can exploit to measure the neutrino mass ordering. But yeah, as I said, in order to do that, we need to access lower energies, because so far we have talked about TeV to PeV events. If you go to lower energies, this is how an event display would look like if your detector is even capable of observing these events. And so it's much harder to interpret the data, and you need the correct detector to do that. Currently, we have deep core that can do it. We heard about Orca. There is the iScope upgrade that would also able to do that. And here in parentheses, Antares, it's kind of at the lower threshold of the Antares energies. So, right, let's measure then oscillations with neutrino telescopes. This is one plot from deep core where you see observed data in black in this histogram, which is a function of L over E, so the term in the oscillation formula. And you can compare it first to this blue line. This blue line is what you would expect if neutrinos would not oscillate. So obviously you can see and convince yourself that neutrinos indeed oscillate. And we can, of course, put that into more quantitative numbers. And this is shown here, oscillation results. We have seen this plot also in the previous talk. This is with 10 years of Antares data. You measure in this two-dimensional plane, the mixing angle and the mass splitting, and you get these black contours. So yeah, it's not very competitive to compare to other experiments, but let's zoom in here a little bit. This is the result also shown before for 1 year of Orca 6 data, and you get this very nice contour. There's now quite a bit better in sensitivity than Antares. And if you zoom in even more, this is a very recent result from Deep Core with 8 years of data. You get this kind of blue contour here, and you see that we get into a regime where we're really competitive with other oscillation experiments, in particular long baseline. So this is the current status, and of course there is a near and longer term future for us. In Deep Core, with the same data set and improved methods that we're currently working on, we expect to get a contour that is around this size here. So this is a projection. For Orca 3 year, you also expect to shrink that down quite a bit more. You get this red contour, and similarly for upgrade, a similar sensitivity with this red contour here. Now, another measurement that I would like to mention, the neutrino mass ordering, right? This is an extremely important question in neutrino physics. This is the question is, from the mass eigenstates, M1 or M3 the lightest? If M1 is indeed the lightest, you call that the normal ordering. If M3 is the lightest, you call it the inverted ordering. And establishing that has extremely important consequences. For example, for the establishment of the absolute neutrino mass scale, for example, as done via cosmology or beta decay, or also for measurements looking at the neutrino nature, is it Dirac or Majorano, so neutrino-less double beta decay. So I try to here explain how we can do this measurement. There are 2 ingredients that you need to know. This is the expected neutrino flux at the South Pole, for example. And one difference you can see is that in general, we expect more neutrinos than antineutrinos. So there's a kind of an asymmetry here. And at the same time, there are differences in the matter oscillations. And this now shows the oscillations for neutrinos and the oscillations for antineutrinos. And you can see here, there is something here that isn't here. So there is an enhancement of the oscillations for the neutrino flavors, for the neutrino particles, but this is assuming the normal ordering. And if you invert the ordering, this happens. And basically this oscillation enhancement then takes place for the antineutrinos. So you can see from this asymmetry, combined with the different fluxes, you get a handle on measuring the neutrino mass ordering. It's a very subtle effect. And we have tried to do that with deep core data with 3 years. And we can do the measurement, but we don't get a really statistically meaningful answer because the data is not yet powerful enough. So this is just a proof of principle measurement that we did. But with the future detectors, either KM3net Orca or the IceCube upgrade, we expect to be able to get an answer on the mass ordering and the order of, like, I don't know, 2, 3, 4, 5 sigma, depending a bit on what exact mixing is realized in nature. Right. Now in the last couple minutes of this talk, I also want to look a little bit beyond standard oscillations and show you a couple interesting particle physics measurements there. One test we can do with neutrino telescopes is trying to test the unitarity of the mixing. Now, what does this mean? This is the standard PMNS 3x3 mixing matrix, as we expected in 3-flavor oscillations, and by construction, this matrix should be unitary. But maybe there's beyond the standard model of physics, for example, including a couple sterile neutrinos that take part in the mixing, which would mean that this matrix is not the complete picture, and it's just a submatrix of a bigger one. The unitarity condition only applies to the full matrix, which means in turn that this smaller matrix does not need to be unitary. And this is something we can test. In neutrino telescopes, you usually do that by just including one additional parameter that breaks the unitarity, and this is the so-called tau neutrino normalization. This just scales the tau neutrinos up and down compared to the mu neutrinos. If it's 0, it would mean complete absence of tau neutrinos. If it's 1, it's exactly what we would expect. This is a measurement we can do very well in neutrino telescopes because it only is possible at energies above 3.5 TeV, which is the threshold energy for observing tau neutrinos. But it's a very challenging measurement because the cross-section are suppressed because this tau lepton is so heavy, and the appearance is in the cascade channel, which is a bit more difficult to measure. But yeah, we have done this in deep core 3-year data. These are these 4 error bars. And you can see what we measure is a bit below 1, but it's consistent with 1. And it just means our error bars are too big to really make an interesting statement here, which just means we need more data. This is how the sensitivities look like. With 8 years of deep core data, what we're currently working on, we expect to get a precision of around 15%. With the IceCube upgrade, we can push that to below 10%, and similar story for Orca, where you also expect to measure that parameter with better than 10% precision. Right, so this unitarity test is kind of a model-independent test. If, on the other hand, you have a specific beyond the standard mixing model, then you can test for that specific model. Some time ago, these 3+1 EV scale sterile models were quite popular, motivated by some anomalies. I think it's slowly fading away. But anyway, let's do that exercise. This is just the same formula as before. You just need to change the mass splitting here, because now you look for EV scale steriles. And what you find is that you get the mixing, maximum mixing at 10 TeV of energy. So now we're moving up again in energy. And also these oscillations are enhanced by matter effects, mostly around 1 TeV. So this is kind of what you would measure, this resonance for sterile neutrinos. And at lower energies, these oscillations just become very fast, and you measure an averaged out effect. This has been done again with IceCube 8-year, putting quite stringent limits on the allowed phase space for sterile neutrinos, excluding even some previous anomalies. You can do a measurement with deep core 3-year. This is the exclusion limits from deep core, and this is Antares 10-year. This just for completeness sake, the projected sensitivity for Orca. Now, last type of measurement, I promise. This is about non-standard interactions. So it's also another beyond the standard model process where you're looking for interactions of neutrinos with the matter in the Earth through different channels. Usually just you have charge current and neutral current interactions mediated by the W and Z boson, but there might be other interactions. How you do that is basically, this is the Hamiltonian, and you just add additional terms here, either diagonal or off-diagonal flavor changing terms. And if you set them to a non-zero value, what you expect is kind of a distortion of the oscillation spectrum. So this is the measurable effect you get. We do that in neutrino telescopes. These are our limits. We have not found non-standard interactions, otherwise you would have heard about it. Deep core 3 years, this is epsilon tau tau and mu mu parameters. This is the epsilon mu tau with IceCube 8-year data. By the way, these are world leading constraints on that parameter, and this is a similar plot by Antares. And yeah, of course, there are many, many more things that I didn't have time to talk about today. We can do much more particle physics. We can do dark matter. We have already heard in this conference a couple of times about dark matter measurements. We can look for other BSM theories like exadimensions, neutrino decay, et cetera, or even do more fundamental physics beyond just pure particle physics. All right, so this now brings me to my summary. I would like to say that neutrino telescopes, they provide kind of unique kind of particle physics laboratory. It allows us to study cross-sections, oscillations, and search for BSM physics. The energies and the baselines that are accessible to us, they're completely out of reach for lab-based experiments. So yeah, as shown, we can measure cross-sections in the TeV to PeV range. We can access oscillations above the tau threshold. We can measure resonances of light sterile neutrinos. And all of that makes us extremely competitive. For atmospheric oscillation parameters, we're kind of in a position to rival dedicated long baseline experiments. For tau neutrinos, we are already world leading. For light steriles, we're also competing with short baseline experiments. And for non-standard interactions in the mu tau parameter space, we also get the world leading constraints. Right, this is it, and thank you.